I want you to picture something simple, something your brain will recognize instantly, without effort, because that's exactly how the illusion begins. You're looking at an image taken from space, and what you see feels familiar before you even have time to question it. Dark shapes that resemble seas, branching lines that look like rivers, coastlines that curve the way coastlines are supposed to, clouds drifting above a surface that seems alive with weather and change. And for a brief moment, your mind settles on a conclusion so natural you don't even notice it forming. You're looking at a world like Earth. That moment, that quiet assumption, is where Titan gets you, because what you're actually seeing is Titan, a moon orbiting Saturn, nearly 2 billion kilometers from the sun, far enough that sunlight arrives weakened, reduced to something pale and distant, yet still just strong enough to illuminate a landscape that seems to echo everything, you know. And this is what makes Titan different from every other hostile place in the solar system. Because most worlds don't pretend. Venus doesn't pretend when it wraps itself in acid clouds and crushes anything that dares approach. Jupiter doesn't pretend when it hides beneath storms and radiation that would tear you apart long before you ever saw a surface. They announce what they are immediately and without ambiguity. But Titan does something quieter, something far more unsettling. It offers you a reflection that looks just close enough to be mistaken for home. Scientists noticed this long before you ever heard the name Titan, especially when data from missions like Cassini-Huygens began to reveal a world wrapped in a thick atmosphere, one that behaves in ways that feel eerily terrestrial, with layers of haze and cloud systems and cycles that resemble weather rather than the static emptiness you expect from a frozen moon. And the more we looked, the more that resemblance sharpened into something almost uncomfortable, because Titan wasn't just vaguely similar. It was structured like Earth in ways that suggested familiar processes were at work beneath the surface of that orange haze. Rivers carve into its terrain. Liquids gather into lakes and seas. Clouds form and dissipate. Seasons shift over time. And every one of those details feeds the same quiet instinct in your mind. The instinct that says, this is a place you understand, but here's where you need to slow down. Because the trap only works if you keep moving too quickly, if you let recognition stand in for understanding. I want you to hold on to that image of rivers and seas for just a second longer, and then begin to strip away what you think you know. Because on Titan, the shapes are familiar, but the substance is not. And that distinction is everything. Those rivers are not carrying water. Those seas are not filled with anything you could drink or even touch safely. And the clouds above are not part of a cycle that sustains life the way it does here. The structure is borrowed, almost perfectly. But the ingredients have been replaced with something entirely different. Something colder, harsher, and fundamentally incompatible with anything you would call home. And that is the part your brain resists, because it wants to compress what it sees into something manageable, something recognizable. It wants to say, this is like Earth, and move on. But Titan refuses to let that simplification hold for long, because every layer you examine more closely peels away that comfort and replaces it with a version of reality that looks right at a distance and feels wrong up close. A world that seems to have studied the blueprint of Earth and reproduced its structure with absolute precision while quietly rewriting every material that makes it function. You didn't misunderstand what you were looking at. You understood it exactly the way your brain was designed to. That's the problem. At Titan's distance from the sun, light no longer behaves like something that defines a day. It becomes a weak presence, a diluted glow that barely survives the journey across nearly 2 billion kilometers before it even reaches the top of the atmosphere. And what remains of it is scattered, filtered, and almost erased by a dense orange haze that wraps the entire moon in a permanent twilight. If you were standing on the surface at what should be noon, there would be no bright sky above you, no sharp shadows, no sense of direction from the sun, just a dim, uniform glow pressing down through layers of smog thick enough to hide the heavens completely, leaving you with the strange and disorienting impression that the world simply ends a short distance above your head. The atmosphere itself would feel familiar on paper and completely alien in reality, because it is composed primarily of nitrogen, about 95%, which sounds almost reassuring until you realize that the remaining fraction is filled with methane, hydrogen, and a complex mix of hydrocarbons that react under ultraviolet radiation to produce that persistent haze, a chemical fog that never clears, never thins, never gives you a clean view of anything beyond it. You would be breathing nothing because there is nothing there your body could use. And even if you were protected inside a suit, the environment outside would not behave like air as you know it. It would feel heavier, thicker, more resistant, pressing gently but constantly against every surface, slowing motion, dampening sound, reshaping how movement itself feels. And then there is the cold, not the kind of cold you imagine from winter or high mountains, but a level of cold so extreme that it changes the basic behavior of matter, where temperatures hover around minus 179 degrees Celsius, a range in which materials you trust on Earth begin to fail. Metals lose their flexibility. Substances that are gases here condense into liquids, and the entire landscape reorganizes itself around chemistry that only makes sense under those conditions. Methane, which on Earth exists as an invisible gas you might associate with a faint smell near a stove, becomes a stable liquid here, flowing across the surface, pooling into lakes, forming seas that stretch for hundreds of kilometers, not as an anomaly, but as a fundamental part of how this world operates. That transformation alone should force you to pause, because it means that everything you instinctively associate with water on Earth, rivers, rainfall, evaporation, accumulation, still exists in structure, but not in substance. And the consequences of that substitution are not subtle. Liquid methane is not something you can touch, not something you can wade through, not something your equipment can safely ignore, because it behaves as a solvent capable of interacting with materials in ways that would degrade or destroy them if they are not specifically designed to withstand it, turning what looks like a calm, reflective surface into something chemically aggressive and deeply hostile. Even the simple act of existing in that environment would feel wrong in ways that are difficult to anticipate, because gravity on Titan is only about 14% of what you experience on Earth, while the atmosphere is significantly denser, a combination that alters how objects fall, how droplets move, how motion unfolds through space. If methane rain were to fall around you, the drops would not behave like rain you recognize. They would grow larger, heavier, yet descend more slowly, drifting downward in thick, deliberate paths, landing without the sharp impact you expect, spreading instead in cold, oily layers across whatever surface they meet. Nothing about this world is chaotic in the way you might expect from something alien. It is structured, consistent, governed by rules that mirror the ones you already understand, but those rules are applied to a different set of materials, under conditions that reshape their outcomes into something that feels subtly, persistently wrong, the longer you try to map your intuition onto Titan, the more it resists you. Because every familiar process carries a hidden difference that only reveals itself when you look closely enough to notice that the comfort you felt at a distance was never built on truth in the first place. You wouldn't hear anything. You wouldn't smell anything familiar. Just a dim orange twilight pressing in from every direction. On January 14th, Lao Chen Lin Wu, something small and fragile began to fall through the sky of Titan. And for the first time in human history, we were not looking at that world from a distance, not guessing, not interpreting radar shadows or infrared echoes, but actually moving through its atmosphere layer by layer, carried by a probe that had no way to correct its path, no way to turn back, only the ability to descend and record whatever it encountered before it reached the ground. That probe was Huygens, released from the Cassini-Huygens spacecraft. And what it experienced during those 2.5 hours fundamentally changed the way we understand what a moon can be. The descent did not begin with a clear view of the surface, because Titan does not allow that kind of clarity. Instead, it started in a dense, opaque atmosphere where visibility was limited and the light already dim. Filtered through layers of suspended particles that scatter and absorb what little sunlight reaches this distant orbit. As Huygens dropped lower, instruments began to register something that, at first, might not seem extraordinary until you realize where it was happening. Wind. Not a static envelope of gas, but active movement, shifting currents, pushing against the probe, buffeting it, tilting it slightly as it fell, revealing that Titan's atmosphere is not passive but dynamic, structured and alive with motion. That detail alone should force a reconsideration, because wind implies gradients, differences in temperature and pressure, circulation patterns that redistribute energy across the planet. And those are not features you associate with a frozen moon at the edge of the solar system. Yet here they were, measured directly, not inferred, indicating that Titan possesses something much closer to a weather system than anything previously observed on a body of its kind. And as the probe continued downward, that implication deepened into something even more specific, because the data began to outline a full cycle. Not just isolated movement, but a process. Methane evaporating from the surface, rising into the atmosphere, condensing into clouds, and eventually returning as precipitation. This is where the familiarity becomes almost unsettling again, because the structure is unmistakable. A hydrological cycle in every meaningful sense, except that the fluid involved is not water, and the conditions under which it operates are so far removed from Earth that every step of the process behaves differently. The droplets that form in Titan's clouds grow larger than those in Earth's atmosphere, shaped by lower gravity and higher air density. And when they fall, they do not rush downward with urgency. They descend slowly, drifting, almost suspended, carried by the thick air in a way that stretches time itself, turning rain into something heavy and deliberate rather than sharp and fleeting. Huygens did not just measure these processes. It moved through them, passing layers where haze thickened and thinned, where temperature shifted, where the atmosphere revealed its vertical structure in gradients that only direct sampling could uncover. And all of this occurred before the surface was even visible, before there was any confirmation of what lay below. By the time the probe reached lower altitudes, the idea that Titan had weather was no longer speculative. It was unavoidable, supported by real-time data gathered during a descent that could not be repeated. At least not yet. And then, finally, the surface emerged. not suddenly, but gradually, shapes resolving through the haze, contours appearing where there had been only uniform brightness, and what came into view only reinforced the conclusion that had been building throughout the descent. This was not a static, frozen wasteland, but a place shaped continuously by active processes, by wind, by rain, by cycles that had been operating long before we ever arrived to observe them. One landing, 72 minutes. That's all we've ever had from the surface. From orbit, the surface of Titan does not confront you with chaos or abstraction. It presents something structured, something legible, a landscape that appears to follow rules you already understand. And that is precisely why it is so deceptive. Radar images returned by the Cassini-Huygens revealed coastlines that curve with the same irregular precision you would expect from erosion shaped over long periods of time. Channels that branch and reconnect like river systems on Earth, basins that collect liquid and hold it in stable bodies that resemble seas, and all of it arranged in patterns so familiar that you could mistake them for satellite imagery of Norway or northern Canada if you ignored the context. Those bodies of liquid are not small, not isolated features that require imagination to compare. They exist on scales that match or exceed some of the largest lakes on Earth, with Ligia Mare stretching across tens of thousands of square kilometers and Kraken Mare extending even further, forming vast dark regions that absorb radar signals in a way consistent with smooth liquid surfaces. The shapes are correct. The behavior is correct. The relationships between elevation, flow, and accumulation all follow the same logic you would use to interpret any terrestrial hydrological system. And yet every one of those conclusions rests on a foundation that is fundamentally different from what your intuition expects. Because the liquid filling those seas is not water, and the rivers feeding them are not carrying anything remotely compatible with life as you know it. Instead, they are composed of methane and other hydrocarbons that remain stable in liquid form only because of the extreme cold that defines Titan's environment. The cycle that moves this liquid across the surface mirrors Earth's water cycle in structure. But the substitution of materials changes everything about how it feels, how it interacts, how it shapes the landscape over time, turning something that looks like a familiar coastline into a boundary between substances that would be unrecognizable and dangerous if you encountered them directly. Even the solid ground resists your expectations once you look closely enough, because the objects scattered across Titan's surface, the rounded shapes captured in the single image returned by Huygens, resemble river rocks so convincingly that they triggered immediate recognition among scientists who had spent their careers studying erosion on Earth. Smooth, rounded, clustered in patterns that suggest transport by flowing liquid. They look exactly like stones shaped by water over time. Except they are not stone in the sense you understand. They are composed of water ice that, under Titan's temperatures, behaves like rock, hard and rigid, capable of maintaining structure where it would melt instantly on Earth. This inversion extends even further when you move into Titan's equatorial region, where vast fields of dunes stretch for hundreds of kilometers, arranged in long, parallel lines that mirror the linear dunes found in deserts like the Sahara or the Namib, matching them in scale, spacing, and overall geometry so closely that the comparison becomes unavoidable. The processes that form these dunes are also familiar, driven by wind patterns that transport particles across the surface, gradually building structures that reflect prevailing atmospheric conditions. But once again, the materials betray the illusion because the sand itself is not made of silicate, minerals, or broken rock. It consists of complex organic compounds. Tholins formed in the upper atmosphere through chemical reactions triggered by ultraviolet light and then deposited slowly over time. There is a detail hidden within those dunes that captures the deeper strangeness of this world. Something that does not align even when you accept all the substitutions and inversions, because their orientation does not match the dominant wind patterns expected from Titan's rotation and atmospheric circulation. For years, this inconsistency resisted explanation until a more complex picture emerged, one in which rare but powerful methane storms temporarily reversed surface winds, reshaping the dunes in ways that override the steady influence of weaker, persistent currents, revealing a system where gradual processes build structure slowly while brief. Intense events redefine it in sudden, dramatic shifts at every scale, from pebbles to seas to entire desert systems. Titan presents you with a landscape that behaves correctly while being constructed from the wrong materials, a world where the equations hold but the inputs have been replaced, where familiarity emerges not from shared substance but from shared structure. The more you examine it, the more it forces you to separate those two ideas, to recognize that resemblance does not imply equivalence, that a coastline is not defined by what fills it, that a river is not defined by what flows through it, and that a desert is not defined by the composition of its sand. Everything behaves the way you expect. Nothing is what it should be. What you see on the surface of Titan already feels like a contradiction held together by familiar shapes and alien substance. But the deeper you look, the more that contradiction becomes layered, because everything described so far exists only at the outermost skin of the world, a thin boundary compared to what lies beneath it. The data that revealed this did not come from images or direct observation of the ground, but from something far less intuitive. Subtle variations in Titan's gravitational field measured during repeated flybys by the Cassini-Huygens spacecraft. Differences so small they would be meaningless without careful analysis, yet precise enough to expose the internal structure of the moon in a way no camera ever could. Those measurements told a story that was not visible from the surface, a story of layers, not just of ice and rock, but of movement and separation. Because the outer shell of Titan does not behave like a single rigid body. Instead, it appears to shift slightly under gravitational influence, as though it is decoupled from what lies below it. And that kind of behavior only makes sense if there is something between the surface and the deeper interior that allows for that motion. Something that can flow. Something that can deform without breaking. Something that acts as a boundary rather than a solid connection. The most consistent explanation, supported by models and reinforced by multiple observations, is the presence of a global subsurface ocean, buried beneath an icy crust estimated to be tens of kilometers thick, possibly extending down 50 to 100 kilometers before reaching that hidden layer of liquid. This is where the nature of Titan changes again, because while the surface is dominated by methane and hydrocarbons, a chemistry that feels incompatible with life as you know it, the interior may contain something far more familiar, liquid water, not exposed to the surface, not interacting directly with the atmosphere, but existing in darkness under immense pressure, insulated by layers of ice that prevent it from freezing completely despite the extreme cold above. And that detail matters, because water is not just another liquid. It is the medium in which every known form of life on Earth operates. the environment that allows complex chemistry to organize, to persist, to evolve into systems that can sustain themselves over time. But water alone is not enough to make this possibility meaningful, because what truly matters is not just the presence of a liquid, but the interaction between that liquid and its surroundings. If Titan's subsurface ocean is in contact with a rocky core, if there are regions where heat from the interior drives chemical reactions between water and mineral surfaces, then the conditions begin to resemble something very specific, something already known to support life in environments completely isolated from sunlight. On Earth, ecosystems exist around hydrothermal vents at the bottom of the ocean, where hot water rich in dissolved minerals emerges from the seafloor, providing energy and chemical gradients that organisms can exploit, forming complex communities in total darkness, independent of the sun. The possibility that similar processes could exist within Titan's hidden ocean is not speculation in the abstract. It is a direct extension of what we already understand about how life can emerge and persist under extreme conditions. But the difference here is scale and isolation, because this ocean, if it exists as predicted, would be completely sealed beneath a shell of ice thick enough to isolate it from the surface entirely, creating an environment that has evolved separately for billions of years without any direct exchange with the atmosphere above. Whatever chemistry is occurring there, whatever structures might be forming or have formed, would do so in a context we have never directly observed, using energy sources and pathways that may parallel Earth's deep-sea environments or diverge from them in ways we cannot yet predict. And yet, despite how compelling that possibility is, it remains inaccessible in any practical sense, because reaching that ocean would require penetrating tens of kilometers of ice under conditions that challenge even the most advanced engineering concepts currently available, making it a destination that exists more as an inference than an objective, a place we can describe, model, and imagine, but not touch. The surface continues to draw attention because it is visible, because it can be explored with probes and instruments. But beneath that thin, deceptive layer lies a second world, one that may be far more relevant to the question of habitability, yet remains completely hidden from direct observation. Whatever is happening down there is happening far beyond reach, beneath layers of ice thick enough to hide an entire world. The possibility of a hidden ocean beneath the surface of Titan gives you one version of habitability that feels almost reassuring, because it resembles something you already understand. But the surface presents a far more difficult question, one that forces you to consider whether life must follow the same chemical rules everywhere, or whether those rules are simply a local preference shaped by the conditions of Earth. On Titan, the environment is so cold, so chemically different, that the structures supporting life here would not function at all. Lipid membranes would become rigid. Reactions would slow to a near halt, and the entire framework of biology would collapse under temperatures that redefine how molecules behave. That limitation led researchers to ask a different kind of question. Not whether Earth-like life could survive on Titan, but whether something entirely different could emerge under those conditions, built from molecules that remain flexible and reactive in liquid methane rather than water. In 2015, a team at Cornell proposed a theoretical structure they called an azotosome, a membrane composed of nitrogen-containing organic compounds that could, in principle, assemble into stable, flexible boundaries in Titan's methane lakes, performing a role similar to the lipid bilayers that define cells on Earth. The idea was not a claim of discovery, but a demonstration of possibility. showing that chemistry does not forbid the formation of organized cell-like structures in such an environment, even if no direct evidence of their existence has been found. That alone would be enough to expand the definition of habitability. But Titan adds another layer to the question through observations that do not fit neatly into existing models. Data collected by the Cassini-Huygens revealed something unusual in the lower atmosphere, specifically in the distribution of certain molecules that should behave predictably if only non-biological processes were at work. Hydrogen, which is produced in the upper atmosphere and expected to drift downward, appeared to be disappearing near the surface in a way that suggested it was being consumed faster than it could accumulate, while acetylene, another compound that should be present in measurable quantities, was found to be unexpectedly scarce. Individually, each of these observations could be explained through complex chemical interactions that do not involve life, because Titan's atmosphere and surface chemistry are intricate enough to produce outcomes that are not immediately intuitive. But what makes the situation more intriguing is how closely these anomalies align with a prediction made years earlier. The astrobiologist Chris McKay had proposed that if methane-based life existed on Titan, it might use hydrogen as a source of energy and acetylene as a fuel, combining them to produce methane as a byproduct, a metabolic pathway entirely different from those on Earth, but chemically plausible under Titan's conditions. The missing hydrogen and acetylene match that prediction in a way that is difficult to ignore, not as proof, but as a coincidence that sits uncomfortably between explanation and speculation. This is where the question becomes less about data and more about interpretation, because science does not move forward by accepting the most exciting explanation. It moves by exhausting the most mundane ones first. And there are many non-biological processes that could account for these observations. Reactions on the surface, interactions with sunlight, catalytic effects involving unknown compounds, all of which remain viable alternatives. The challenge is not the lack of possible explanations, but the lack of direct measurements that could distinguish between them, leaving the current evidence suspended in a state that invites curiosity without allowing confirmation. What Titan forces you to confront is the possibility that life, if it exists there, would not resemble anything you recognize. Not in structure, not in chemistry, not in the conditions it requires. And that recognition carries a deeper implication, because it suggests that the definition of life itself may be broader than the example you are familiar with. That what you consider essential might only be essential in one specific context. The surface of Titan is not just a hostile environment. It is a testing ground for ideas about biology that extend beyond Earth. A place where the boundary between chemistry and life may be drawn differently, if it is drawn at all. The data doesn't prove anything. It just refuses to stay quiet. Everything you know about Titan comes from distance, inference, and a single brief contact with its surface, which means that for all its apparent familiarity, it remains largely unvisited, a place mapped in fragments and reconstructed through interpretation rather than direct experience. That gap between what has been observed and what actually exists on the ground is what the next mission is designed to close. Not by repeating what was done before, but by changing the way exploration itself works on this world. Dragonfly is not a lander that arrives, transmits data, and fades into silence. It is a machine built to move, to lift itself from one location and carry its instruments across the landscape, turning Titan from a single point of contact into a network of sites that can be compared, sampled, and understood in relation to one another. The choice to build something that flies is not an engineering novelty. It is a response to the specific conditions of Titan, where low gravity and a dense atmosphere create an environment in which flight is not only possible but efficient, allowing a vehicle to traverse distances that would be impractical for a rover and to reach locations selected not by proximity but by scientific value. Each hop of Dragonfly is designed to cover several kilometers, lifting off, navigating through that persistent haze, and landing again in a different region where it can analyze the surface, measure chemical composition, and search for patterns that cannot be detected from orbit. The target is not random terrain, but carefully chosen sites, such as impact craters, where materials from beneath the surface may have been exposed and mixed with organic compounds already present above, creating environments where different chemical pathways intersect. That intersection is critical because it represents a rare opportunity to examine conditions where water-based and methane-based chemistry might have briefly interacted, even if only in the distant past, offering a natural experiment that cannot be reproduced in any laboratory. Dragonfly carries instruments capable of analyzing these materials in detail, including mass spectrometers designed to identify complex organic molecules and determine how they are structured, how they vary across locations, and whether they show signs of organization that go beyond random assembly. The mission does not assume that it will find life. It is not built around that expectation, but it is designed to recognize patterns that would force a reevaluation of what chemistry can become under Titan's conditions. The challenge lies not only in the scientific objectives, but in the environment itself, because operating on Titan requires systems that can function under extreme cold, where conventional materials behave differently, where lubricants can fail, where electronics must be protected from temperatures that would disrupt normal operation, and where the only reliable source of power comes from the steady decay of plutonium-238, providing energy in a place where sunlight is too weak to sustain solar systems effectively. Every movement, every measurement, every transmission back to Earth must be executed within constraints that push the limits of current technology, making the mission as much a demonstration of engineering as it is an exploration of an alien world. And yet, even as Dragonfly represents a step forward, it does not eliminate the uncertainty that defines Titan. It amplifies it, because the more precisely you measure something, the more clearly you see what you do not yet understand. Each new data point has the potential to resolve existing questions or to introduce new ones. To confirm that Titan is merely a chemically complex but lifeless system, or to reveal structures that suggest a deeper level of organization, something that sits on the boundary between chemistry and biology without fitting neatly into either category. The outcome is not predetermined, and that uncertainty is what gives the mission its weight, because it is not just about filling gaps in a map. It is about testing whether the assumptions used to interpret that map are valid in the first place. What makes Titan different from every other destination in the solar system is not the extremity of its conditions, but the way those conditions are hidden beneath a surface that appears so deceptively familiar, a landscape that echoes Earth's forms while replacing its substance. A world that presents itself as something you recognize until you look closely enough to see that every element has been rewritten. Dragonfly will move through that environment, crossing dunes made of organic particles, landing near features shaped by liquid methane, sampling materials that have never been touched directly before. And in doing so, it will begin to answer questions that have remained open since the first images were returned decades ago. But even then, even with a machine moving across its surface, Titan will not give up everything at once, because its most important features may still lie beyond reach, buried beneath ice, hidden within chemical systems that do not reveal their structure easily. existing in forms that challenge the categories used to describe them. What Dragonfly can do is narrow the possibilities, reduce the uncertainty, and replace speculation with evidence. But the deeper mystery, the one that makes Titans so compelling, will remain tied to the way it mirrors something familiar while refusing to be understood on those terms. A flat horizon, rounded stones, a sky you can't see through,